Modeling continuous 3D rotations requires a coordinate system that doesn't break under pressure. When we try to map these dynamics using standard real or complex numbers, the math collapses into flat, two-dimensional projections that lose critical phase information. The solution is the quaternion. While 3D graphics engines use them to calculate smooth rotations, their algebra defines a four-dimensional coordinate system handling three-dimensional phase natively. By operating across 4 dimensions, it simultaneously encodes amplitude and phase. This prevents mathematical singularities causing gimbal lock, preserving the physical geometry of a rotating system. This specific geometry provides a scale-invariant language capable of mapping 3 distinct tiers of reality: the microscopic quantum state, the neural networks of biological life, and the cosmos's large-scale topological structure. To understand how structure survives entropy and maintains stability at any scale, we have to look at how the universe utilizes quaternionic phase. At the microscopic baseline, quantum computing faces a functional bottleneck, mapping a massive set of n-dimensional quantum inputs down to a single stable output state. The quaternionic quantum perceptron processes these inputs by applying a unitary operator across them, evaluating their exact phase and amplitude values simultaneously to prevent data loss during processing. It resolves this data using a Hopf projection. The network takes abstract four-dimensional state vectors and projects them onto the recognizable surface of a 3D block sphere. This reduces phase entropy to yield a measurable state without destroying the underlying quantum information. The efficiency of this artificial network stems from its use of quaternionic algebra, the same mathematical framework found in the relativistic equations governing physical matter. We see this geometry at work in the Dirac-Eck equation, which models the fundamental behavior of subatomic particles. Within this framework, the spinorial structures of an electron emerge directly from quaternionic rotations. These spinorials act as the fundamental carriers of the particle's phase. At the quantum baseline, structural integrity relies on locking onto a stable phase state to resist the effects of entropy. Moving into the macroscopic world, these identical geometric principles govern real-time adaptive control in complex environments. Engineers use the quaternion spiking neural network to process the natural delays that occur between signals, evaluating multiple presynaptic inputs simultaneously within a quaternionic space. This allows the network to calculate adjustments across 6 degrees of freedom in real time. The manipulator arm tracks erratic 3D trajectories smoothly, avoiding the stuttering and overcorrection that occurs in standard control systems. Biological systems operate under these same geometric requirements to maintain their physical structure. At the molecular scale, DNA functions as a long-range phase memory structure. Its helical architecture is designed to stabilize and distribute phase information along its length. Living networks are governed by the biological stability constraint. If phase coherence drops below a critical mathematical threshold, the system loses its structural integrity. When phase entropy exceeds this limit, it undergoes catastrophic topological collapse. The physical helix rapidly unspools into disconnected points. Stability at the biological scale is the result of a system successfully suppressing its own internal phase entropy. As we scale up to the cosmic manifold, these same coherence fields organize into larger structures. The E-model interprets stable macroscopic objects and cosmological structures as reality knots. A reality knot is defined as a coherent, non-contractible topological loop embedded within the dynamical field of spacetime. This 3D surface plot illustrates the intensity of the energetic coupling field required to maintain one of these knots against the expansion of space. The depth of the central peak and the surrounding purple depression represents the energy holding the knot's structure together. This collective phase field functions like a massive version of the weighted sum in a quantum perceptron, operating at the scale of the universe. Mathematically, a reality knot is the coherence-weighted product of billions of individual quaternionic configurations acting as one stable entity. This concentrated coherence field fundamentally modifies the local geometry of gravity. The coherence factor, C of x, directly rescales the metric tensor of spacetime. In regions of high coherence, the local physical geometry physically warps and tightens. When we substitute this modified geometry into standard Friedmann equations, we find that universal expansion is driven by the internal phase organization of the field. Our large-scale cosmic structures are effectively the macroscopic shadows of quaternonic phase synchronization. Aligning these three mathematical models reveals a shared structural pattern across 10 orders of magnitude. The underlying topological rules governing structure remain constant. Only the complexity and scale of the phase field changes. Observe the primary structures we have mapped from the quantum tier to the cosmos. Whether we are programming an artificial quantum qubit to isolate a data pattern, or engineering a spiking network to stabilize the motion of a robotic arm, or mathematically modeling the topological expansion of cosmological spacetime, quaternonic phase coherence, expressed through the factor C, remains the consistent mathematical requirement across all three. The preservation of structure at any scale demands continuous phase alignment. Where coherence fails, reality unties.